Clarice, actually, I think we met 2 years ago at one of our longevity biotech workshops, just after you did a seminar. And recently we were in touch again because you're just building something absolutely outrageous with many, many different application spaces. Ask her for her one-pagers on all the different application spaces. And today you're going to focus on the nanotech one. So take it away, Clarice. Thanks for coming.
Thanks for having me here. So in our nonprofit, where is the previous speaker? We are also doing things in a completely open science way, and I do think that that's the way to go. So I would like to propose that we think about nature as the foremost nanotechnologist, right? And in fact, I'm going to go a little bit beyond and propose that we think about nature as the foremost quantum engineer. So I'm here to talk to you about a overlooked, understudied, and many times misunderstood degree of freedom in biology, which is the fact that biology seems to be responding to weak magnetic fields in a way that is consistent with that being driven by a quantum phenomenon. And as you see here, all the basic machinery of the cell is tweakable via this knob. With weak magnetic fields on the order of the magnetic field produced by your cell phone, you can both up and down regulate all of those processes. I am going to tell you how data on this has been studied for the past decades, and I'm going to argue that we need to break clean with this old way of taking data and build new instruments to actually really take rational advantage of this very cool knob in biology. And this is not a biological, it's not a basic science curiosity. All of those fields there, and I'm going to talk about a lot of them, including space travel, have the potential to be drastically altered once we start paying attention to this degree of freedom in biology. So let's go. In order for me to explain to you how this works, I need to talk to you about spin. So spin is a fundamental property of nature, and it's as fundamental, say, as charge and mass. In the same way that charge measures how an object interacts with an electric field, mass measures how an object interacts with a gravitational field, spin measures how an object interacts with a magnetic field. Atomic nuclei have spins, electrons have spins, and spins are usually represented with an arrow. Arrow up or arrow down means different ways that a spin can interact with a magnetic field. In my presentation, the yellow arrows are going to represent electron spins. So here's what it happens chemically. There's a chemical reaction happening, and at some point the chemical reaction comes to a crossroads. At that point, the chemical reaction is effectively going to look for the spin state of one particular electron. If the spin is down, the chemical reaction continues through one pathway. If the spin is up, the chemical reaction continues through a completely different pathway, yielding completely different final products. Spin is a quantum property, and in the presence of a magnetic field, a spin is going to be put in a quantum state known as a superposition. For those of you who have never taken quantum mechanics, I suggest that you think about superposition as a dimmer switch. A spin can be a little bit up and a little bit down, but it's both at the same time. And different magnetic field yields different positions of this dimmer switch. The overall consequence of this fact is that an electron that is in a particular superposition put in by the magnetic field given by the blue magnet is going to yield certain products in this chemical reaction whose combinations, whose proportions are going to be given by the position of this dimmer switch. A different magnetic field, for example, the green magnet, is going to yield a new combination of products. Now, I'm going to make 3 comments. They're highly technical, but that's fine. So the first comment is the fact that even though that process is very, very fast, it happens between nanoseconds and microseconds timescales, but it's still before thermalization kicks in. That process of sensing the magnetic field is very, very fast, but the consequences of that, because it all happens downstream from this intersection, the consequences of that are felt macroscopically and at time scales much, much longer than the time scales during which the quantumness survives. Okay. The second point that I would like to make, this is completely well understood. It's very counterintuitive, but here, for this type of phenomenon, more magnetic field is not always better. The magnetic fields that can actually alter the final products of this type of chemical reaction are relatively small, relatively weak, up to more or less 10 times the magnetic field produced by your cell phone. And finally, it turns out that this, chemists have been aware of this for decades. They don't call it like this, but once physicists started looking at this phenomenon, they started calling it quantum sensing. Actually, this is indistinguishable from the way that technological quantum sensors use to sense magnetic fields. So here, the superposition, the quantum state, is actively used as a resource. Okay, that's a true quantum phenomenon happening in chemistry, and there's no doubt that this happens in test tubes and at room temperature. Now, as I mentioned, all those biological phenomena there have been shown across the tree of life, and they have been shown to be tweakable by weak magnetic fields in a way that is consistent with this phenomenon. I can put a lot of papers there, but sometimes people get it, what I'm saying, when I show this image there. So it turns out that if you grow cells, or in particular tadpoles, in chambers, in hypomagnetic chambers that shield the very tiny magnetic field of the Earth, things go bad in biology. You have a higher rate of malformation. So if you don't believe this, we're actually doing an open science version of that experiment. This was taken by my colleagues. My lab is doing a public replication of that, and we want people to know that weak magnetic fields make a difference for life on Earth. And again, if you want to colonize Mars, you'd better know what the magnetic field in Mars is to know if you can reproduce in Mars. And people have been finding magnetic fields that do stuff for very, very long. There are companies that increase the yield of lab-grown meat by magnetic fields that are known to reduce cancer. And we can also play this game of trying to find magnetic fields that do stuff. We can take cell incubators, put boxes that block the magnetic field inside the incubator, or apply magnetic fields, and we see things that people have been seeing for decades. For example, your cell's cytoskeleton changes after application of a magnetic field weaker than your cell phones, and in fact, you see also that you can increase or decrease the production of cellular oxidants in the presence of magnetic fields. But all of this is very haphazard. When people find magnetic fields that do stuff, it's a little bit like being in a haystack, grabbing a little bit of hay and finding a needle, right? Data you cannot compare because there are many parameters: field direction, frequency, strength. Can we do better? And in fact, I think we can, because given that this phenomenon is presumably altered by the type of chemical reactions that we can model using the tools of quantum physics, I propose that we build a quantum-like experiment to look at those phenomena using a quantum lens. Those experiments are composed of 4 ingredients. It's a microscope, coupled to coils, everything synchronized down to the nanosecond, because that's the time scales that we care about, and with very good way, with single photon detectors for another reason. And you can call it a glorified microscope, but it's actually a quantum instrument that can look at biology, look at quantum degrees of freedom in biology in a unprecedented way. This is like the blueprint of the microscopes, and we're finishing around to build those instruments that can unambiguously establish or refute whether quantum is being used by nature to function. Again, this is not a basic science curiosity, and we have been able to put together a collection of quantum biology briefs, and we've been able to truly find meaningful connections between quantum biology and from drug development to AI to quantum computing. And we really think about quantum biology as really the first piece of a domino that can unblock many other scientific pursuits. So I'm going to finish by saying, may the quantum be with you.
that tau protein aggregation is one of the possible common effects.
That's correct.
Do you think that there's any relevance to that research to longevity research, or
Absolutely. Absolutely, right? Tau protein is very clearly related to longevity, but you can also mess up with other cellular parameters by applying carefully crafted weak magnetic fields. You can, again, change oxidation parameters, change how fast cells divide, change cellular respiration, change glycolysis rates, and all we really need is a code book on how to do so rationally, and for that you need those quantum instruments.
Thank you so much, Clarice.